Okay, so here we are, lecture 6 on power series, still in a section 11.8. I wanted to just do a couple more examples, just to make sure we really have the right idea. This is, we've got power series and we're looking for the radius and interval of convergence. So I've got a power series down here. The sum n equals 1 to infinity of negative 1 to the n. Times x minus 5 raised to the n over n times 3 to the n. And, well, are we expanding around here? We're expanding around 5, right? So a is equal to 5. So as we saw in previous videos, this thing is either going to converge for all x, in which case the radius of convergence is infinity. It's going to converge only at x equals 5, in which case the radius of convergence is 0, or there's some finite non-zero radius of convergence, and it's going to converge on some interval centered at 5. Okay, so let's see. Again, this is not a geometric series because of that n, and it's not a good root test because, well, n's not raised to the nth power. So I would use the ratio test again. So let's use the ratio test to get started. So we're going to look at the limit as n goes to infinity of negative 1 to the n plus 1, x minus 5 to the n over, sorry, n plus 1, the n plus first term here, over n plus 1 times 3 to the n plus 1. And that's all over negative 1 to the n, x minus 5 to the n, all over n times 3 to the n, right? And we're taking the absolute value of that. So we're taking that limit. Again, we can simplify the denominator. We can invert and multiply. And what happens with those absolute values, where the absolute value of negative 1 to a power is just 1, so we can ignore that. And the only other non-positive term is x minus 5. So we're going to have some absolute values x minus 5. Inverting and multiplying, it looks like we get n times 3 to the n, absolute value x minus 5 to the n plus 1. And in the bottom, we're going to get n plus 1 times 3 to the n plus 1, absolute value of x minus 5 to the n. And this simplifies to what? This simplifies to the limit. N goes to infinity of, okay, well, 3 to the n over 3 to the n plus 1 is 1 over 3, right? So I get n plus 1 times 3, and then the x minus 5 to the n plus 1 over x minus 5 to the n is just x minus 5. And now I can evaluate this limit. N over n plus 1 goes to 1, and everything else is fixed with respect to n, so I get x minus 5, absolute value of that over 3. So the cutoff point is going to be when that thing's equal to 1, right? So if it's less than 1, it converges absolutely. If it's bigger than 1, it diverges. So converges absolutely if x minus 5 over 3 is less than 1. So that's the same thing as saying x minus 5 is less than 3, right? Or negative 3 is less than x minus 5 is less than 3. So here, at this point, we can actually see what the radius of convergence is. Because if I'm going to solve for x, I'm going to add 5 to both sides. I'm going to have 5 minus 3 and 5 plus 3. That 3 is the radius of convergence. So this is going to have a finite non-zero radius of convergence, and that's going to be 3. And you can see that the interval, we're going to have 5 minus 3 less than x less than 5 plus 3. So we've got the possibilities for the interval of convergence. Well, it's going to go from let's see. It's going to go from, I want red, from, it's going to go from 5 minus 3, which is 2, to 5 plus 3, which is 8. We just have to decide whether those endpoints are in there. It diverges whenever x minus 5 over 3 is bigger than 1. So that's the same with x as x bigger than 8 or x less than 2. So we just have to figure out now what's happening at 8 and 2. So let's do that. So at x equals 2, I have what's going on. At x equals 2, I'm looking at this series. N equals 1 to infinity of negative 1 to the n. 2 minus 5, which is minus 3 to the n, over n times 3 to the n. And minus 3 to the n can be rewritten as minus 1 to the n times 3 to the n, right? And that's over n times 3 to the n. And minus 1 to the n times minus 1 to the n is what? That's just 1, right? That's either they're both negative or both positive. Either way, it's just 1. And the 3 to the n's cancel. And I get n to the infinity of what? 1 over n. So, converges or diverges? Yeah, diverges. Harmonic series. So it's the harmonic series. So x equals 2 is not in that interval. So we have an open parenthesis over here. And now let's look at x equals 3. So x equals 8, the other endpoint. So this is n equals 1 to infinity of negative 1 to the n. 8 minus 5 is 3, right? 3 to the n over n times 3 to the n. And the 3 to the n's cancel. And I get n equals 1 to infinity of negative 1 to the n over n. And this converges, right, because it's the alternating harmonic series. The alternating series test tells us it converges. So that means this endpoint is in the domain, and there's our interval of convergence. Okay, so let's do one more example since we have. Okay, so I've got a new series up here now. Sum n equals 1 to infinity of 2n plus 1 raised to the nth power over n to the nth, and that times x minus 1, x plus 1 to the n. So have you noticed, what is my a in this case? What am I expanding around? I'm expanding around minus 1, right? So it's either going to converge for all x, it's going to converge only at x equals minus 1, or it's going to converge on some interval centered at minus 1 with or without the endpoints. So let's figure this out. Now this is a good example for the root test because everything's raised to the nth power. So let's look at the root test here. So in the root test, I'm looking at the limit as n goes to infinity of the nth root of the absolute value of the nth term. Oh, guess what? I don't want this to be absolute value. This is just regular. When I'm taking the limit, it's an absolute value. It's not harmonics. It's not a strict power series if I have an absolute value there. But I'm taking the absolute value of this term, so I get 2n Okay, so let's simplify that absolute value a little bit. So that's going to be the limit. N goes to infinity of the nth root of. So the only thing that could possibly be negative is the x plus 1. So that's what I'm going to. And so now I can take the nth root. And I get 2 to the n plus 1 over n absolute value x plus 1. And now, this thing here is a rational function, degree 1, numerator and denominator, so that limit is 2 over 1, which is 2. And x plus 1 doesn't change with n, so this is going to be 2x plus 1. And again, for the root test, it's going to converge absolutely if that's less than 1, right? If 2x plus 1 is less than 1, and it diverges if it's bigger than 1. So that less than 1 is the same as x plus 1 less than 1/2. Now at this stage, that's the same as negative 1/2 less than x plus 1 less than 1/2. And you can see that the radius of convergence is going to be 1/2, because I just am going to add negative 1 to both sides to solve for x. Right? So when I add negative 1, I get negative 1 minus 1/2 less than x less than negative 1 plus 1/2. So the interval, well, we know the endpoints of the interval. We don't know if they're in there yet. Interval of convergence is, it goes from negative 3/2 to negative 1/2, and it may or may not contain the endpoints, so we have to check now to see if it contains the endpoints. So let's try x equals negative 3/2. So we're looking at the sum, n equals 1 to infinity of 2n plus 1 to the n over n. And negative 3/2, that's going to be negative 3/2 plus 1 is negative 1/2 to the n. And that can be rewritten as the sum, n equals 1 to infinity. Let's write this like this. 2n plus 1 over n to the n times negative 1 to the n times 1 over 2 to the n, which is going to be sum n equals 1 to infinity of negative 1 to the n times 2n plus 1 over 2n to the n. So what's happening here? Notice that this term here goes to, well, that's 1 to the infinity, 1, but it's bigger than 1. This is always going to be bigger than or equal to 1, right? So this term does not go to 0, so this diverges. This diverges. So that endpoint is definitely not in there. And let's look at the other one. X equals negative 1/2. We're looking at the sum, n equals 1 to infinity. Let's write it like this again, n plus 1 over n to the n. And at x equals negative 1/2, that's 1/2 to the n, right? So that's 1 over 2 to the n, which is the sum, n equals 1 to infinity of 2n plus 1 over 2n to the n. And again, this diverges because this is always bigger than or equal to 1, so it does not go to 0. So it diverges by the divergence test. So the interval of convergence is here, and this is a good place to stop.